We just started discussing the absolute p-center problem. I gave you the definition, and I gave you a finite dominating set property that supplies an optimal solution, but we were not able to go through the proof. So what we have here is we again have a network, say N, with vertex set V, arc set, was it E or A? I guess it was E, yeah. We're talking about undirected edges, and we defined the function f of x by the maximum weighted distance wi dx vi I from 1 to n, where dx for a point set x is the minimum of dx vi is the minimum of the distances between elements of x and vi. And of course we're interested in the case where x is restricted to have finitely many or p points. And for the case p equals 1, we have already solved the problem. That's the one center problem. And for the case p equals n, there's a trivial solution. You just place one center on top of every vertex or every demand point. And for p greater than n, again, that solution will be good enough. So the non-trivial case is for the case p between 1 and n, strictly between. This problem is NP complete. The proof is due to Kariv and Hakimi. The recognition version is NP complete. As an optimization problem, people refer to it loosely as NP hard. So the proof is due to Kariv and Hakimi. SciAm, Journal of Applied Mathematics, back in '79. That's the paper. Okay? So in the single facility case, we observed that there's an optimal solution which occurs at a breakpoint of those edge-restricted piecewise linear functions. And we refer to them as intersection points. So we say a point x in some edge of the network N is an intersection point if there exists distinct vertex indices I and j such that the distance Vix is equal to the distance Vjx, and any epsilon movement or any movement from x by a small distance amount epsilon in any direction, meaning of the two available directions, makes at least, well, makes one of the distances dvi or dvj strictly larger. Okay, that's the definition of an intersection point. It simply corresponds to, this is an edge-restricted function. It corresponds to a point that looks like this. So that when you look at the maximum of these two distance functions, they happen to become equal at a particular point x, such as this one. And if you move a little bit to the right, then one of them gets worse, it increases. If you move a little bit to the left, again, one of them gets worse. Okay? So that's the definition of a intersection point.
Why do we need the second part of the definition? Can you move to the next?
Because we want to distinguish that from the following case. That's also an intersection, but in that case, if you move from x this way, both actually get smaller. Okay? You don't want that. You want it only this way. Okay? Of course, that's an intersection point as well, but not one that we are interested in. Okay? For us, intersection points are of this kind. Okay. So let's define P to be the point set consisting of all intersection points on the network. Now, the number of elements or the number of points in P is how many at most? For a given edge, you may have up to n squared, order of n squared intersections. Each pair of indices may supply an intersection point in a given edge. So n squared per edge. Of course, many of them may not be defined, but that's the worst that can happen. And on the entire network, of course, you have n squared times however many edges you have, the number of edges inside your edge set. So the cardinality of P at the worst is bounded above by a polynomial function of the problem data, n squared times the number of edges in the network. What's the largest number of edges you can have in the network for an undirected network? N squared, or order n squared, actually it's n times n minus 1 over 2, but that's n squared. So this can go up to n fourth in general, okay? All right. So let's define, say, V prime to be the union of the vertex set and the set of points in the intersection, the set of intersection points. Did I give a different name to it, or did I give any name to it before? No? No name? Okay. Let's just call it P prime or whatever you want to call it. How many members of this? This is going to be your finite dominating set. There will be at least one optimal P-center solution coming from this set. Okay? And there are, of course, so many in P, and V contains n, so this again has n squared E. members. Okay? And here's the theorem. For the absolute p-center problem, which looks for a minimization of the f of x function defined here, where x is any point set coming from the network and the number of points that you have is restricted to p, where p is between 1 and n. So for the absolute p-center problem, where each point in the set is a point of the network and the number of points is p, there exists, or there is an optimal solution, x star, such that x star is a subset of v prime. Here's a question for you. Can there be an optimal solution which is not a subset of v prime? This is an existence type of. For the p-medium problem, there was an optimal solution which was a subset of the vertex set. But we allowed for other possibilities, that some edge interior points could be optimum, or could be in there. How about in this case? Yes? No? Are you sure? Anybody? Any other opinion?
No.
No? How many people say no? How many people say yes? How many people say no opinion? Huh? Abstain, okay. The answer is yes, there could be optimal solutions that are not subsets of v prime. That's a possibility. But I'm not going to go into that right now, but maybe at the end of this lecture, if you remind me of that, we may go into it, okay? All right, let's just prove it this way. The proof is similar to what we have done for the p-medium problem. So let's just take, for example, x bar to be an optimal solution. Let x bar be an optimal solution to the absolute p-center problem. If x bar is a subset of v prime, there's nothing to prove. We're done. Okay? So if x bar is not a subset of v prime, then there's at least one element in it which is not in v prime. Partition, in this case, v into p subsets where the ith subset, say, vi prime, vi. So we're partitioning the vertex set V into p subsets where the ith subset vi consists of vertices vj for which the closest distance between x bar And that vertex is defined by the ith element xi bar of x bar with ties broken in favor of smaller indices. So we simply put into the ith subset all those vertices which receive service from the ith center in the optimal solution. If a vertex has tied closest distances to different centers, you just put that vertex into the smallest VI set, into the smallest indexed VI set. Okay? All right, so with this partition, solve a one-center problem, an absolute one-center problem defined by minimization of the maximum of Wi dx Vi. You minimize over x in the network. Actually, x in the network, where the vertices under consideration are those. Okay, that's it. Let's change that to Vj. Are those in partition Vi. Okay, these are J, and we are talking about the ith subproblem. So solve a one-center problem of this sort for each I, 1 up to p, and let xi star be an optimal solution for the ith subproblem with xi star coming from V prime, because for the one center case we know that there's such a solution. Okay? Now we have the following. If you begin with f of x star again, it's by definition the maximum of Wi dx sorry, I meant x bar. Let's begin with x bar. F of x bar, which is by assumption an optimal solution, is the maximum of weighted distance where I goes between 1 and n. Now, when you partition, this is the same as subdividing the vertex set, the range 1 to n, into subsets. Okay? So I am looking at the ith subset here. Does everybody agree with this? Well, this is a simple operation here. All I'm doing is the vertex set here is the union of VI's, I going from 1 to P. So I'm separating the maximum operator into subsets, VI. For the ith subset, I'm simply looking at the same function, find the maximum of it, but I repeat this for each partition, and whatever the maximum of all these partitions will be the same as that one. Okay? Hatice, This is J such that Vj in Vi. Okay, because you questioned that before. It's just a short notation for that. Okay. All right. Now this is the same as the same thing. Except that I'm going to replace that one with the actual distance. Okay? Because for the ith subset, this closest distance is defined by xi bar from the definition of what we have done.
Going to be min max?
No, we have no min here. This is by assumption optimal, so I'm just evaluating the f function here.
We're taking the single distance which gives the value. Okay.
Right, this is just the definition of the f of x function with x, of course, given by x bar, and the other ones are simply definitions, okay? Nothing more than that. Okay. Now here, when you look at this part, that part is greater or equal something. What is that greater or equal? If you replace xi bar by xi star, which is by assumption the one center, where am I? Where is that? Did we say that? Oh, okay. And let xi star be the optimal solution for the ith subproblem. Okay. For the ith subproblem, when I solve this optimization problem only for vertices in the ith subset, I get a certain solution. And that solution is xi star. And by assumption, it's coming from V prime. So if you replace xi bar with xi star, because this is an optimal solution for this subproblem, obviously its objective value will be less than or equal to that. Okay? So this is greater or equal the same thing computed relative to optimizing solution xi star. That's again because, by definition, xi star is an optimal solution, so its objective value, its f value, should be less or equal to the f value of the other solution. All right, continuing with that. That last expression is greater or equal the maximum over I between 1 and p, again, of the weighted distances, wj, replace it with capital. Since each distance small d is greater or equal the closest distance, obviously that's true. Okay? Now that thing is equal to, if you recompose the partition into all vertices, what is this? I don't need double max here, sorry. Single max. In other words, I just got rid of the partitioned or decomposed max operators. I just combined them into a single max operator over all vertices. Before it was on different subsets, now it's over all vertices. what's this? By definition, this is f of x star. Ataberk. That's just by definition the f function evaluated at x star. And what do I know about f of x star? I know that it's greater or equal f of x bar, because by assumption x bar is an optimal solution. So it must beat the other one or equal it. It cannot be better. All right, so I pointed the wrong way. This one is some solution to the absolute p-center. This is an optimal solution. So this is at least as good as that one. So either you have equality or less than. Okay. So hence all inequalities hold as equalities, because we began with f of x bar and we ended up with f of x bar with all these inequalities, and accordingly x star is also an optimal solution. Note that, of course, x star is a subset of v prime. Okay? Okay, so this reduces our search space from an infinite space into a finite space. So I can actually enumerate all possibilities if I know nothing better. And if I enumerate all possible p-element subsets of v prime, then we're talking about choosing p-elements out of however many elements you have in v prime. That would be a finite search. So you choose a particular p-element subset of it, you evaluate the f function, and then you keep doing this by retaining the smallest one up to that point. Okay? And finally, you find a p-element subset which gives the optimum or the smallest objective value. Now, so this is, of course, how much? Well, it's in the order of, I don't know, that's, we had how much here? N squared E elements, and we're talking about choosing p elements out of that. That's quite a large number. If p is close to either 1 or n, this will be okay for enumeration purposes, but if p is somewhere in the middle portion, this will be a large number, okay? Whatever it is, you can compute it. Okay. However, nevertheless, there's some comfort in this because it actually gives you a finite algorithmic method. Now, you don't know what that method is. Nevertheless, we can do that. Can we open that window for a while? Because it's a little bit too warm here. Huh? Okay. Solving the p-center problem via a sequence of set covering problems. That's what I'm going to describe to you now. you don't only solve one set covering problem, but you have to solve a number of them until you converge to the P-center problem solution. Okay? Now, many of you may be familiar already with the set covering problem. If you're not familiar, that's okay. I'll cover what that is. Okay? So let's first define an optimal value for the P-center solution. For fixed P, let's define Rp to be the minimum objective value of the P-center solution, where X is a subset of V prime. I can do that now without losing optimality, with X being equal to P. Actually, let's not do that. Let's just keep it the way it is. Rp is the minimum objective value of the worst case weighted distance, okay, of the minimization of f of x. Rp is certainly a positive number, unless p equals n, in which case it's 0. Okay? Well, if you're cold, we can close that, huh? I guess. There's some movement taking place, so I felt that there must be something, wrong. Okay. Consider the following equivalent problem. We again minimize some variable r subject to f of x being less than or equal to r, which means, of course, if f of x is less than or equal to r, then each weighted distance is less than or equal to r. So you've got this. Wi times that is less than or equal to r, or that one, where again x is selected from n with cardinality restricted to p. Okay? So the output of this optimization is again Rp.
Did we use,
Well, the optimal value is Rp. Yes.
did we use R instead of Z?
Yeah, we can use z, but I'm going to use the term radius, so r is more related to radius than z. Okay? You can use z; it doesn't matter. Okay. These variables are dummy variables. You can name them whatever you want to. Okay. So with this equivalent problem, let's define a related covering problem. In the covering problem, I fix R. In the former problem, here, R is not fixed. It's a variable to be minimized. In this one, I pick a value for R. Of course, it's a non-negative, well, it's a positive value. Okay? And then I want to minimize the number of points I find. So I'm minimizing the cardinality of the point set X, subject to, I again want every vertex to be covered by at least one point in this point set. with x again in N. Now let me have your attention for a moment, because even though the relationship is quite obvious, I think you should pay attention to what's going on here. First of all, over here, R is a variable. The output is a point set, an optimal set, whose best objective value happens to be some number, RP. Okay? In this problem, we picked a value for R. And what we wanted to do is, we wanted to satisfy these constraints by picking some points in the network. So we wanted to cover every vertex Vi in the sense that we wanted to have some member of X within this much of R over Wi distance of that vertex. Obviously, Vi may have more than one such points satisfying this particular distance, but it doesn't matter. As long as I have X, at least one, I'm going to be in good shape. So we're trying to cover every vertex Vi within a distance of R divided by the appropriate weight. And we're trying to do that by picking the smallest number of points that does the job. Okay? Now, if my R, if the picked R happens to be less than RP, what would you expect here as a solution?
Greater than P.
Greater than P. Yeah. If R, for example, suppose RP is, say, 10, and you happen to pick 6 here. In that case, of course, to be able to cover everybody within a distance of 10, you were able to use P points to do that. But now, when you reduce that radius, you're not going to be able to accomplish the same thing by using, again, P points, because if you were able to do so, you would have obtained 6 here, rather 6 or something less, rather than 10, right? So the relationship is quite obvious. Well, to me, it's obvious. I think if you think about it, it will be obvious. If your R happens to be larger than RP, you would expect to have a minimum cardinality solution of P or less points. Yes. If it is too large, in fact, maybe you can do the entire job by picking a single point, okay? If it's large enough. All right, so let's give a name to this. This QR will be something dependent on R, the value I picked. Q of R is an integer, okay? Because the objective value is a cardinality here, okay? So when I solve the problem, the covering problem, if QR is an integer, if this happens to be greater than P, then what do I know? I'm asking the same questions that I just asked a few minutes ago in reverse order. R is greater than RP. So if the number of points you find is more than P, then obviously R is not enough to allow you to cover everybody with P points. Okay, so in that case, R is smaller than RP. So whenever QR happens to be greater than P, then we know that the picked radius is too small. Yes?
Isn't that, since we select R, isn't that the otherwise, like if R is smaller than or equal to RP, then...
No, but I don't know RP. I'm going to solve this problem as a related problem. So whatever I obtain here, I want to be able to make conclusions on the basis of that without knowing RP. Here I'm just making an inference on whether I should increase R or decrease R to solve the next related problem. Okay? Does that make sense? Normally we don't know RP. Of course we will somehow converge to it. But is the conclusion correct here? If QR is such that it's strictly larger than P, obviously your R is too small to obtain a P-centered solution which gives you the same R. Okay, so obviously R is strictly smaller than RP. I think we can make that conclusion. And in that case, of course, more than P points are needed to cover all demands within a radius of R. In other words, to satisfy these constraints. So in this case, increase R somehow and resolve the problem. If QR is less than or equal to P, then R is the other way around. In other words, it's sufficiently large to permit you to place either P points or less than P points to cover. So in that case, of course, we know that we can do the job with less or equal P points, so we might as well decrease our R. And we might want to decrease R and solve the covering problem one more time to see what happens. When do we stop? So this essentially tells you the main idea. You either increase or decrease depending on the most recent solution you get for the covering problem. So let me restate this in the following way. So we're looking for the smallest R, and let's call it R star, such that the covering problem yields a solution less than or equal to P, solution value less than or equal to P, while any reduction in that radius by even a tiny amount, epsilon, gives you larger than p. So you're looking for a particular value of the radius which permits you to place not more than p facilities, while any further reduction in that radius will not allow you to cover everybody with only p facilities. Okay, you will need at least one more additional facility.
Is this for any epsilon or for given epsilon?
For any positive epsilon.
Then we are looking for the exact of.
Yes. This is the definition of the exact solution, or how you can extract the p-centered solution from the set covering from the covering solution. I haven't gotten into set covering yet. It's the covering problem, but it's not set covering yet. Okay. Well, this is conceptually. I guess maybe if that sinks, then we can certainly go ahead and start playing with this. Now, we're essentially out of time, but let me just point out one thing here. This is a play with R, okay? So what you might want to do in this case is, assuming that you know some lower bound, a natural lower bound is 0 for R. So some lower bound, say A, and some upper bound, say B, for the R value. What's a natural upper bound? You pick any P facilities, place them. They don't have to be optimal. Evaluate the F function at those P facilities. Whatever that F value is, that's your R, okay? That's just a feasible solution. So your R will be somewhere in this range, or your RP will be in this range. And you begin with this, and then, for example, you begin with the middle value. Depending on what outcome you get, you either truncate the upper portion or the lower portion, okay? So each time you do this, you truncate your most recent interval into two parts and delete one part, which actually in case steps it will get you into a fraction of the actual RP value that you're looking for. This would not be an exact method. This would be an epsilon approximation method. You can certainly converge to it as close as you wish. However, what we're going to do next time is we're going to solve this actually exactly. Okay?